So, hi everyone. In this appendix to the lecture, we are going to prove some of the um, theorems or lemmas or claims that whose proofs we left out, so to save time and also concentrate on the more conceptual material. Okay, so as I said, we are going to prove some of the things we left out from the lecture. So we talked about Adeles, and we had these a couple of easy claims which I'm not going to prove. Say this claim, which talk about the relation of the Riemann-Roch space with the Adele Riemann-Roch space. And this claim, which it gives the simple properties of Riemann-Roch spaces of Adeles. But the thing I do want, one of the two results I do want to prove now is this lemma. So this lemma tells you that if you take a divisor smaller than the other, a smaller or equal than b, and you look at this quotient, right? So this is the Adele Riemann-Roch spaces corresponding to B, and that's corresponding to A. And since A is smaller or equal than B, then this is a subset of that. And actually, both of them are K vector spaces. So this is a subspace of this K vector space. So what this lemma tells you is that the dimension of the quotient as a vector space over K captures exactly the degree difference between the two divisors. Right, and we actually saw that already. I mean, we saw an expression like an algebraic structure that also, an algebraic object, particular K vector space actually, whose dimension is also exactly this degree difference. And if you remember, that was these truncated Riemann-Roch spaces that we had. So if you had B and A as in our case, and S was the union of the support of these two divisors, then we proved that the dimension of this as a K vector space is precisely the degree difference. And afterwards, we proved some inequality, by the way, if you remember. So the dimension of the quotient of the non-truncated, the good old Riemann-Roch spaces, is only upper bounded by the degree difference. So we do really like the equalities because it tells you that you capture something, but we don't quite want to work with these truncated versions of Riemann-Roch spaces, and we prefer to go to Adeles, which are more complicated, but as I said in the lecture, they somehow give you a good mix of global and local properties of your function field, and we rather have this as an explanation for the degree difference. And you will see when you saw in the lecture, and you will see in what we prove next also, that you can take this like kind of a long way. But so let's prove this lemma. And we are going to use what we know. I mean, we are going to use the fact that we already know that this degree difference is captured as the dimension of this quotient, right? I mean, we want to understand, again, moving backwards, this is a number, and we want to understand it algebraically. It's a shadow of something, of some object. So we know that it encodes this object, and instead of doing everything again and trying to figure out how this object is related to this number, we are just going to relate these two objects. So in particular, we want to prove that there is an isomorphism as K vector spaces of this subspace that we want to know whose dimension, and this subspace which we already know its dimension. Okay, so we want to prove some isomorphism here. I mean, these are very different objects. These are Adeles or quotients of Adeles, and these are functions, but nonetheless, we want to prove some isomorphism between them. And like usually, if you have, generally speaking, if you have some subspace, maybe it looks like a field. You have a space over another space, and if you usually want to prove something like that, then what you should do is somehow come up with a natural homomorphism from U to W, prove it's onto, and show that the kernel is V. Right? When using the first isomorphism theorem, you have this isomorphism. In our case, it's not clear where to start because both sides have quotients, but it turns out that the right place to start is from here. So let me be more precise. So we are going to define a map from the functions in the function field, so from F, to A. So we are going to start from here. So from functions to Adeles. So we are going to to define a function from F, which is actually a superset of that, right? To the Adeles, and the map is as follows. So you take an element in F, and the Adele that you're going to send it to at its pth location, that the principal prime divisor prime divisor P, you're going to put X if P is in S. S is again the union of the two divisors, A and B, and 0 otherwise. Right, so you're going to kind of put X exactly on the support of A and B and 0 otherwise. That is a valid map from functions to Adeles, because indeed, I mean, just to make sure, we do need always to make sure that our Adeles are actual proper Adeles, namely, for only finitely many prime divisors, you have negative valuations, but here you have almost always zeros, only finitely many non-zeros, because A and B have finite support, and so that is an Adele. Good. So we have this map, which I just rewrote here. And this is clearly a k-linear map, right? If you have an x and y and you sum them up and it goes to the sum and so forth. And what I'm claiming is that if you restrict it to these truncated Riemann-Roch spaces, because currently it's defined from F, then I'm claiming that it maps this truncated Riemann-Roch space into lambda of A. And similarly, with the same argument, this Riemann-Roch space into lambda of B. Right? I mean, going back, I want to find somehow a map from here, actually, from here to here, but we are kind of we started with a map from F to Adeles, and what I'm saying is that if you restrict yourself to here, then you end up here. Okay. So let's see why this is true. We're going to prove this with A, but it's the same thing if you have B instead. So if you start with X that is in this truncated Riemann-Roch space, then what does it mean? It means that for every prime divisor in S, you have the valuation of X at P is plus the valuation of A, like the coefficient of the divisor A at P is non-negative. And I can now extend it from S to P and replace X by T of X, because T of X outside of S is 0. So outside of S, the prime divisors which are not accounted for here. Outside of S, you have a 0 here, which means an infinite valuation here. So, this constraint is going to be satisfied. And within S, T of X is X, and so this implies that. Right? And if you look at it for a second, this is precisely the ticket for T of X to be in the lambda of A. Okay, so in pictures, we have the following. We started by defining a map from F to the Adeles. We called it T. And we showed that if you restrict the map to the Riemann-Roch spaces, or truncated Riemann-Roch space of B to S, then T will map that restricted domain to lambda B. And also for A, but here I'm only using that. We're going to use A in a second. So, right, so currently we have a map from here to here. I want a map from here to here. So the next step will be let's consider the natural way of taking our map and getting a map which we call T bar from here to here. Right, and then we'll do so, we'll just apply T and then project. Right, take the coset of lambda A. Okay, so at least we have this map, which we call T hat. And what I'm claiming, so maybe let me go backward and see it in the picture. What I'm claiming is that this map is onto, and the kernel is precisely LA of S, LAS. And this kind of picture is a kind of the standard mathematician's way of saying that. It says that this map factors through LAS, namely the kernel is LAS implies or is equivalent to saying that in order to describe this map, you first describe what happens to cosets and then extend. Okay. But that's just like a diagrammatic notation, so it's not really important. What we are going to prove really is that this is an on T bar is an onto map with kernel LAS. Okay, so let's start with the kernel. So what is in the kernel of T bar? So right, so these are all the elements that T maps to lambda A, right? Because if you look backwards, the kernel, uh, so an element here is going to the kernel if T bar of X is zero, but the zero in this space is this coset, so it's essentially the same thing as saying that T of X is in lambda A. And what does it mean for T of X to be in lambda A? Well, for any P in P, for any prime divisor, VP of T of X plus VP of A is non-negative, right? And now let's consider two cases. So if P is not in S, it's kind of similar to before. If this little p is not in S, then you have a zero here because T of X outside of S is zero, and that constraint is satisfied. And so you don't really have to worry about those little p's that are not in S. So we can write it again saying that the kernel of T bar is all of the elements in this truncated Riemann-Roch space, such that only for those p which are in S, VP of X, I changed T of X to X because on S it's the same thing. VP of X plus VP of A is larger or equal than zero. And technically that's not precisely LA of S, but if you replace it by F, then this is the definition of LA of S. So what we really have here is LA of S intersection with LBS, but their intersection is of course LAS because it is contained in LBS. Okay. So that proves that the kernel is what we want. Now we need to prove it's an onto map, it's an epimorphism. So let's show that T hat is onto. T bar is onto. So if you go back to the picture again, given a coset here, we want to find an X that's mapped to that coset, right? Okay, that's a bit more tricky. So let's take an element in lambda B to start with. By the weak approximation theorem, we are guaranteed that there exists some function x in F such that it satisfies these finitely many constraints. S is a finite set, and what are the constraints? So I want VP. So my requirement is that, well, my requirement is this thing. Let's read it from here. So VP of X minus this number, minus this function, sorry, the function that sits at the Pth location at beta. I want that to be larger than this particular value that I'm interested in. And note that uh, uh, because the way T was defined, this is exactly the same as VP of Tx minus B, or minus, yeah, or minus BP. You can have it or not have it. Yeah. So the weak approximation theorem can only worry at least for now for finitely many prime divisors. So for prime divisors outside of S, we are just going to observe easily that we still have the same constraint, the same inequality, because VP of Tx minus BP, what's written here, well, Tx is zero there, so it's precisely VP of minus beta P, but that's VP of beta P. And because beta is in the lambda space of B, that's at least minus VP of the divisor B, which is zero, because outside of S, you only have zeros, and it's also zero for VP of A, because S is the support of the reunion. And so again, you can see that actually for all places you have that this inequality holds. Right? So this means that Tx minus beta is in lambda A, right? Because it satisfies all the requirement for it to be in lambda A. Or put differently, we have that T bar of X is beta plus this lambda A. Okay, so we proved that our map is onto, Namely, we found an element X that is being mapped to, we started with a beta. So we took an element here, which is beta plus lambda A, and we find an element X that is being mapped by T to that element. However, we only put it so far, we only know so far that X is in F. We don't yet know that X is in this truncated Riemann-Roch space. So we still have to do a little bit of work. So we need to prove that X is in LBS. And indeed, so we just go place by place. For every P and S, we have that VP of X is at least the minimum between VP of X minus beta at location P and beta at location P, the usual add and subtract trick that you have, and using the triangle inequality. Now, VP of X, so this expression is at least minus VP of A. That's what we had before. And VP of beta P is at least minus VP of B because beta is in lambda B. And so in any case, it's at least the minimum, and the minimum is it attained at B because B is the larger divisor. So the minuses gives you the smaller values. And that's exactly what you wanted to prove. That implies that X is in LBS. Right, and as I said, once you know that, then you apply the fourth isomorphism theorem and you're done. So to summarize, we've just proved that the dimension as a k-vector space of lambda b over lambda a, whenever a is at most b, is the degree difference between the two divisors. So now the second lemma that I want to prove, and that's all we kind of left out from the lecture as far as Adeles goes, is we just proved this lemma that tells you that the dimension of this quotient is the degree difference. Well, there is another lemma that tells you that if you add to each of these lambda spaces f, right? Recall f is embedded in the space of Adeles, so that's a sum within the k-vector space of Adeles. So the dimension as a k-vector space of this quotient captures not the degree difference, but the degree minus dimension difference, what we call the efficiency difference. So this is a deficiency of B and this is a deficiency of A. And kind of interestingly enough, this algebraic object captures the difference between these two parameters, which are of very much interest to us. Okay, if you recall, they capture how much deficiency you have. So degree B is how many degrees of freedom you allowed in your divisor, and the dimension is how many functions actually obey those degrees of freedom. So for the proof, it is going to be essentially a proof by picture. And I'm going to use the fourth isomorphism theorem, which looks like this, okay? I think we talked about it last time at some point. Any case. So let's see. So this is the proof by picture. I'm going to add some words to it and everything's written in the notes, but let me start with the picture. So let's start actually with these two spaces. So let's consider kind of a mix and match. You look at lambda of A, so these are Adeles, of the smaller divisor, and this is the Riemann-Roch space L of B. So it's a bigger divisor. So it's a bigger divisor, but these are only functions. These are Adeles, right? It's kind of a weird mix. And what I'm claiming, and I'm going to prove that afterwards, is that the intersection of these two is exactly the Riemann-Roch space of A. That's quite easy, but I'm going to show that. And their sum is, you can also write it as an intersection, namely as lambda A plus F. You see, this is where plus F kind of comes from, and lambda B. Okay, so here you only have these lambdas now, not L, but you have this F also. And now again, because this is an intersection of two things, let's consider the two things, the corresponding two things. So you have these two spaces, and let's consider their sum also, right? So trust me for now that these two equality holds and hold, and let's proceed. So what I'm claiming now, so let me maybe write here. So right, so we just showed that we are interested in this thing, right? In this green thing. We want to understand the dimension of this this case vector space over this one. And by the third isomorphism theorem, this is the same as taking this one. I mean, by the, yeah, it's actually, maybe by the second isomorphism theorem, it is equal to that one, which is a weird creature that we never looked at. But by the third isomorphism theorem, we know that this is the same, or it is isomorphic too. Oh, I got an ugly. This or that. Right, so the third isomorphism theorem tell you that right, the dimension of this thing is the dimension of that thing over the dimension of that lower block. Now, the dimension of this thing, of this orange or whatever, this brown arrow, is what we had, right? What we just proved, the previous claim, the degree difference, because this is the quotient of the lambda spaces. So this gives the degree difference. So let me write delta deg. And well, this one, well, I don't know what that is, but I know that it is isomorphic again by the second isomorphism theorem to this arrow, to this extension. And that extension, if you remember, is the dimension difference. Well, it's actually just obvious. It's just the dimension difference. And that's it, right? So this thing that we care about is the difference between the degrees minus the difference between the dimensions, which is precisely what's written here. Right, the difference between the degrees minus the difference between the dimension. Okay, good. So that's approved by picture and it works. The two things I owe you is why these two equality holds. So let's go over that. So let's start with the easier one, this one. Why is the Riemann-Roch space of A is precisely the lambda space of A intersection with Riemann-Roch space of B. So okay, so one of the directions is okay. Actually, here I prove it just immediately. So right, good. So what is L of A? So we saw already that L of A is lambda A intersected with F, right? For a given fixed divisor, the Riemann-Roch space is precisely the lambda divisor, the lambda space of that divisor, the intersection of all functions. It's almost a tautology. And okay, so you can write L of A as L of A intersection L of B, because L of B is contained L of A. And using that, you can replace L of A with lambda A intersection F. And then you can, if you want, you can put the brackets in this, on these two last expressions. And then you can see that F actually doesn't matter at all because it contains lambda B, sorry, L of B. And so you are left with lambda A intersection L of B, which is what we wanted. This one is a bit trickier. So let's do that. So we want to prove this equality now. We want to prove that this kind of weird mix of the lambda space of A plus the Riemann-Roch space, L space of B, is exactly the same as if you would intersect the lambda space of B with this F plus lambda space of A. Now, one direction is obvious, like this direction is obvious. And the reason is, both of them are there. So L of B is here because it's both in lambda B and both in F, therefore in the sum. And lambda of A is certainly lambda B because B is larger, and it's certainly here because you have the lambda A sitting here. So the harder part is to show why everything in the intersection of these two sits in the sum of these two. Okay, so let's take an element in the left-hand side, and because it is in this part of the intersection, you can write it as alpha plus x, where alpha is from here and x is a function. It also holds that alpha plus x in the lambda space of B because it's in the intersection. So it's here, and that's why we wrote it in this way, but it's also in the lambda space of B. And this implies, because alpha is in the lambda space of A, and therefore in the lambda space of B, it implies that x is in the lambda space of B as the difference. Alpha plus x is there, and alpha is there, so the difference between them, x, is also there. But x is a function, it's not just an Adele sitting somewhere. So actually x is in lambda B and in F, which again, by the previous claim that we actually never quite really proved, it's in the Riemann-Roch space of B. So X is in the Riemann-Roch space of B. And so what did we get? We get that alpha plus X, the element that sits here, you can write it as, well, alpha is in lambda A, and X is in L of B. So you wrote every element here as an element here plus an element here, which is precisely what we wanted to do. Good. And here, if you want to look at the notes, you have the proof by picture I actually wrote down in words, but it's two instantiations of the second isomorphism theorem and one of the fourth isomorphism theorem. Okay, so, but I think the proof by picture is much easier to grasp. Good. Yeah, so that's all for the missing proofs from the Adele part of the lecture.